fully factor p of x equals 3x cubed plus 11x squared minus 40x plus 12. So to solve this problem, we'll apply our four-step process to apply the factor theorem to factor a polynomial. And in step one of that process, we'll use the rational zeros theorem to help us determine potential roots. Okay, so step one of our process is to determine a root of our polynomial and its corresponding factor. So the rational zeros theorem is going to help us out here by telling us that the potential roots that we should check are going to take the form of p over q, where p comes from the factors of the constant term. So in this case, that's 12. Its factors are plus or minus 1, plus or minus 2, plus or minus 3, and so on. And q is going to come from the factors of the leading coefficient. So those are plus or minus 1 and plus or minus 3. Okay, so basically, our potential roots must have their numerator as one of these numbers and their denominator as one of these numbers. So the first thing I always recommend is to check positive and negative 1, since those are just easy to check. In this case, just by looking at the numbers, I can tell that p of 1 is not going to be 0, so 1's not a root, and p of negative 1 also will not be 0, so negative 1's not a root, which means x minus 1 and x plus 1 are not factors of this polynomial. Now, generally, I recommend that you move next to the next possible integer potential root before checking fractional ones. So that means we check the next p value instead of checking the next q value. So we'll check plus or minus 2 over plus or minus 1, which just gives us plus or minus 2. Starting with positive 2, let's plug 2's in for all the x's. We'll end up with 3 times 2 cubed plus 11 times 2 squared minus 40 times 2 plus 12. Okay, so 2 cubed is 8, so this is 3 times 8, which is 24. Then we end up with 11 times 2 squared, so 11 times 4, which is 44. Then we have minus 40 times 2, which will give us minus 80. Then we have plus 12. So 24 plus 44 is equal to 68. We have 68 minus 80 plus 12. And you may be able to tell from this expression, if we add 12 to 68, we end up with positive 80. Then we have this negative 80, so those will cancel and give us 0. So that means that 2 is a root, and therefore x minus 2 is a factor. Okay, so now we're on to step 2, where we divide our polynomial p of x by the factor we've just found. So that factor that we've just found is x minus 2. I'm going to do this synthetically just to save some time and a little bit of space as well. And keep in mind we can do it synthetically because our divisor has the form x minus a, where a is 2. So I'll write the 2 outside of our synthetic division symbol. Then we'll bring down the coefficients of the polynomial. So they are 3, 11, negative 40, and positive 12. So we'll have 3, 11, negative 40, positive 12. Now the first step of our division is to bring down the 3, or the first coefficient. 2 times 3 gives us 6. Now we're going to add 11 plus 6, not subtract. Remember, in synthetic division, we add the numbers vertically. So 11 plus 6 gives us 17. 2 times 17 is 34. Negative 40 plus 34 is negative 6. 2 times negative 6 gives us negative 12. 12 minus 12 is, of course, 0. So now we can interpret our result here. 0 is the remainder, negative 6 is our constant term, 17 is the coefficient on the x term, and 3 is the coefficient on the x squared term. So our quotient, q of x, is 3x squared plus 17x minus 6. So we can rewrite our original polynomial as the product of this quotient and the divisor that we divided by to get this quotient. So we'll have 3x squared plus 17x minus 6 times x minus 2. Now step 3 is to repeat our process until we come out with a quotient that is quadratic. So if this quotient, q of x, wasn't already quadratic, we would try to guess at a root of it, and then once we found the root and corresponding factor, we would divide this expression by that factor again, hoping to get a quadratic result. In this case, the result's already quadratic, so I'm just going to rewrite our quotient like so. And now we can move right on to step 4. So step 4 is to factor the quadratic. Now this is a messy trinomial, so we have to apply the long factoring method. We need to know the product of the leading coefficient and the constant term. So 3 times -6 gives us -18. And now we're looking for two numbers that multiply to -18 and add to +17. Let you think about that for a second. You should come out with 18 and -1. So that's what we're going to split our x term into. We'll split it into 3x squared plus 18x minus x minus 6. Now we're going to factor by grouping. So from the pair of terms on the left, we can pull out 3x to leave us with x plus 6. From the pair of terms on the right, we can pull out -1 to leave us with x plus 6 as well. Now the brackets match, which means we're on the right track. So we're going to be left with 3x minus 1 times x plus 6, like so. Okay, so now we've factored the quadratic. We can rewrite p of x as the product of the quotient and the divisor that we divided by to get the quotient, but we'll write the quotient in factored form. So we'll write this quadratic as 3x minus 1 times x plus 6, and then of course we still have that factor, x minus 2. Okay, so that is the solution to this problem. Our fully factored p of x is 3x minus 1 times x plus 6 times x minus 2.